All right, so we have our first speaker, Paolo Coppi, talking about the Silla quest. Yeah.
Yeah, all right. Thanks a lot. I just wanted to point out, remind people that there's this Silla quest survey that exists, and I talked about it somewhat in one of the subgroups, topics groups, and I was hoping to have more updates than I said I would have, but I don't quite have it because I had some family issues to deal with in the meantime. But in terms of training sets and data that we can use to prepare for LSST, there's sort of ZTF. That's based in the north. In the south, we have this Silla quest survey, which I just want to point out some characteristics and show you a few things and suggest that we can do something with it. And give the punchline first, to process all this data require a lot of computational power. There's still some processing to be done, but there's spare computation power. And one of the issues that was discussed in some of the top, subgroups for our collaboration is we don't have enough computing power necessarily to cross-match a billion objects from Gaia with other catalogs. There is enough computer horsepower at Yale to do this. And I'll show you some of the results of that, but it could be that we could do some of the work for this collaboration on the sort of cluster associated with this. Okay, so what's the Silla quest survey? It's a successor to the Palomar quest survey, which took the Palomar Schmidt and replaced the photographic plate holder with the CCD camera with 112 CCDs in the late 90s, early 2000s. This is the camera that discovered Sedna, which is a minor planet, which caused Pluto to be demoted in status, and it did some other interesting things. While it was going on, they discovered that the Palomar site isn't that great. So Charlie Balte was the PI. The project went down to Silla and ESO and got his hands on that Schmidt, which is a later model compared to the Palomar one. Has got better seeing and a better sight, and things worked a lot better. And there were glitches in the CCD electronics. Those all got fixed. So the Silla quest is what the Palomar quest survey should have been, and see, it's quite useful. The main characteristic is this shows you the coverage in terms of our declination, and the thing to take away is these purple regions, and I don't have a pointer. Let's see, and the mouse isn't working either. The purple is more than 90 to 300 visits. Yellow is more than 300, and the dark blue is from 500 to 1,000. So there is a lot of coverage. Okay, the Silla quest survey does not have multiple filters. It has one broad filter, complementary strategy to other surveys. That was designed to let in as much light as possible, so you can cover as much sky and go as deep as possible. You lose the color information, but if you're into variability surveys and selecting AGN based on variability, that's a big advantage. Also, the cadence was not allowed to change, unlike some other experiments where every 3 months a new group came in and rejiggered everything. So there's nice uniform coverage. That's uniform, and you'll see that that's useful for selecting AGN. Okay, and the filter is the long dashed line. The solid line, which is basically the sum of the G and R filters. So because of that, if you have simultaneous G and R, which is what you get from Sloan photometry, you can predict within 1% what the quest magnitudes are. So you can cross-calibrate it and match it to other surveys, and I'll show you some examples of that. The balance time coverage, because it was a supernova survey, I should have said that, to get rid of asteroids, you take an image and then wait for 2 hours, and if it's a solar system object, it'll move off the galaxy that you're looking at, and the asteroid could otherwise mimic a supernova. So we have coverage from 2-hour timescales, and it's a sort of rolling cadence, 2 hours every few days, for weeks, and then repeated when the object comes in. And this is a typical supernova discovery light curve, including, I can't move the pointer, but pre-discovery data. If you look back to the left of the peak, there's quite a lot of data there, because a quest is rolling across the sky, sort of like ZTF, okay? And it's a 1-meter telescope, but if you stack things at 100 exposures, you can actually get down to 24th magnitude. That means that if you have an object where it's periodic, for example, you can do some crazy stuff like for R. Lyrae. Okay, and there are lots of things Quest is good for. I won't go here finding low surface brightness objects. And the pipeline is an ensemble photometry pipeline, okay, where you take the nearest neighbors and you try and match between frames and do relative photometry, and then at the very end, you match it to an external system. of which now they're very good external systems from like the Delve survey, Sloan, and Pan-STARRS. And internally, you can get scatter less than 5 million magnitudes for a bright object. And these objects here, it shows an end-to-end test matching to the Sloan and Stetson. And we're sort of getting 2% errors. And if you work through the inherent errors that are quoted for those surveys, they're sort of at the percent level, which means, and if you add things in quadrature, as a result, the LSST Quest is also at the sort of percent level, okay? And to verify photometry, we went over our O'Leary stars, and it works. And one thing we've done is, a little bit what Matthew Graham was talking about, we now have variability maps, light curves, okay? And this is a sky map showing that we have 180 million objects, okay, over basically minus 80 to plus 25 degrees with more than 12 points. 12 points doesn't sound like a lot for a light curve, but the distinguishing characteristic of IGN is it shows long trends. So if you take a random walk, and we've got 6 years, so take the square root of dt and multiply by some time step over a year, you see that a typical AGN might change by 0.2 magnitudes over 6 years. And that's pretty big. And you can find that over with 12 observations, because you might have 3 or 4 observations during the first epoch. You can all co-add them, and then you can take 4 observations at the end and co-add them, and then you should be easily able to detect 0.2 magnitude variations. And it works, I think, okay? So that's what it looks like. So we use this to make a preliminary AGN catalog, especially with contributions from Paolo Sanchez and the Chilean group, using basically the same things that are used by Alerce for classification. The latest input set includes features from guys like proper motion Gaia, proper motion WISE colors, and Delve RGIZ filter values and colors resulting from that. Okay, but before all the Delve and all those WISE colors are put in there, it's a hierarchical classifier, and the first thing that the classifier wants to determine is whether or not this variable is, this object is variable. And then once we decide it's variable, we try and classify it into different types of variable objects. Okay, and the current AGN sample of pure, we think pretty pure objects is 1.6 million, and it's being used as right now as the input catalog for the 4 most changes spectroscopic AGN survey. So that's a 4-meter ESO survey that's going to cover all the LSST area, and so we're going to get hopefully 1 point something million AGN spectra to play with. Okay, because it goes over a large area with different amounts of coverage, the purity is somewhat hard to evaluate. Okay, but if I look at, and I'll show you some examples, the EFEDS, E-Rosita area in the milli-class catalogs will go deep, and we think the associations are reliable. Milli-class is not always reliable, but it should be a stripe 82 because they're spectroscopic Sloan measurements. Okay, they have a 70% match rate. Okay, so that's a lower limit, and when I show later, I was getting sort of 90%. All right. And the key thing to think about for science that we can do here is if you take LSQ and DTF, you can throw it in there, EFEDS, which is X-ray selected, and milli-quasar, they all have sources that are not in each other's catalogs, and probably some of them are real. So the surveys are seeing different classes of objects, which is not a surprise. Okay, here's what that catalog looks like now. There's a gap at minus 30 because there were some cuts on Delve sources that have since taken away, and that's artificial. The key thing is that in well-sampled areas like on the equator, we can hit 140 AGN per square degree, which is comparable to some other surveys. So we're going pretty deep, okay? For fun, you can cross-match with milli-quasar survey, and you see these dark bands? Those are all the surveys that went into milli-quasar, okay? Like stripe 82. So we're doing in principle better. We may be adding noise, but we're at least doing as well as some of those surveys. And here's a confusion matrix on the bottom right-hand corner. And the main thing is what fraction of the training set AGN were recovered as AGN, and that came out as 93%. Okay? And with the main contaminant or misidentification being CDs. Okay? Which is not a surprise, which is always a problem to deal with. And that doesn't mean that's actually how pure your survey is, but at least you're on the right step. One thing that was everybody's worried about is, and the current survey here is doing aperture photometry. We're going to try some other stuff later, but is you could get killed by non-variable galaxies that are misphotometered. And the key insight that Paolo Sanchez had is an AGN has a damped random walk, sort of red noise, and if you misphotometer an AGN, it kind of, or a host galaxy, or a galaxy with no AGN, the variations are kind of night to night, and they're sort of Poisson, and they don't look like the power spectrum that you get from an AGN, so that galaxy contamination is fairly low. Of course, the number density of background galaxies is huge, so you have to worry about that, and that could be a contaminant, okay? Yeah. And then if you go matching, to show you the kinds of things that we're finding, most of the objects that come here are partly because their WISE criteria turn out to be galaxies, and the things that we're not seeing are things that have galaxy kind of colors that Eurysita sees something, and we don't, and that's not a surprise. That's probably the case of like an X-ray bright optically normal galaxy, or a highly obscured AGN. Either way, the host light swamps the AGN light, and a variability survey with some threshold limit will not pick that up. So we're blind on that, and LSST at some level will be blind to that too. If we do difference imaging, we can improve on that. We'll see a quest. The supernova survey has difference imaging, but it was done in a kind of crude manner, so we're working on that. But it'll be important for Lucia Quest and LSST to develop a better difference imaging pipeline. So what do the objects look like? If you cross-match to the eRosita public deep pre-survey EFEDS, okay, the match rate is order of 40%, okay? That could mean that 60% of the objects are junk, but I would argue that's not the case because some of them, objects that are not in the EFEDS are in milliquasar, which means you have Sloan spectra, and they're classified as AGN, so they're real. So an interesting thing that we could think about as a group is what kind of selection techniques are we going to apply, and what do different catalogs that are based on different wavebands bring to it, and how do we reconcile all this? And we're all probing elephant from different regions and seeing slightly different things, so we need to think about that. So the cool thing is the redshift distribution. Most of the objects actually between redshift 1 and 2, which is not what old optical surveys would do. If you select for blue objects, they should be between 2 and 3. If you select on X-rays, they're between order redshift 1. So we're more colorblind than a normal, like UV selected Sloan survey, which is good. So that was the promise of variability. We don't care about colors. Do that. And if you look down at the bottom, we see that most of the objects there have luminosities greater than sort of 10 to the 43 ergs per second, which means we're missing all the low luminosity Eurysita objects, which is not a surprise. And the typical columns are around 10 to the 21, so not very obscured. And in principle, even though the redshift is between 1 and 2, if you look at it, there's a tail that goes all the way out to a redshift 5, so you can pick up objects. Here's more sort of verification. I wouldn't compare it to the too much text. To the DESI early data release, and there were 270 objects classified by LSQ as AGN, and 241 of them were obvious QSOs, 19 were galaxies, and 7 EDR said were stars, okay? But those stars were CVs, okay? And the galaxies, 19 galaxies, when you look at them and plot them on the bottom right corner in W1 minus W2 versus an optical color, they're lying, the dark blue dots, I think the red dots, are clearly in the AGN space. So maybe DESI screwed up its classifications, and I've talked to other people, and you have to take what's coming out of the early data release pipelines with a large grain of salt. Having the kind of time variability coverage that Lucia Quest provides, you can do a much better job of random walk parameter determination, especially if you can add in data, longer term data from, for example, SDSS and Stripe 82. And the red shows you constraints from just Stripe 82 data. So second, and blue is LSQ, so not so good for long-term stuff. But if you combine the two, you can nail the break much better. And the black small circle at the center is on there. So I have a student, hopefully we'll look at that, make it better. It's a good archival data set also for not garden variety things, but tidal instruction events and QPEs. Here's something that Mathew Graham had pulled out in a paper once, saying here's a weird object that looks like that. So on this side, and it's weird, it's totally smooth and doesn't vary at all, but it has a humongous jump. This is on the left, this is Lucia Quest, and on the bottom I superpose Lucia Quest on Catalina, and they basically agree perfectly, except Lucia Quest is much smaller error bars. And it's a perfect straight line, which means it's exponential decay. So this is something weird. It's not your normal AGN. Lucia Quest was only for 6 years, but it still can fill in gaps. Some of you are involved in searches for binary quasars. So here's a random binary quasar candidate I pulled out from Catalina, the Catalina paper. Red is the Catalina data. The green is the ZTF data. The black curve is the cycle that was quoted on there. And the blue is Lucia Quest data. And it doesn't really fit well, the cycle, I would argue. And there are like 6 points very high near the minimum. And here's a zoom in, maybe that works. Okay. That doesn't fit very well. And the ZTF also has a peak sort of where the minimum should have been. So I would not call this a very strong candidate. That's a typical 100-ish point Lucia Quest light curve, and it's 16th, 18th magnitude. The error bars are pretty small, sort of less than 0.1. So you can do something real with that. So, so there's good data, I think. And here's a sky map of showing where Lucia Quest has good coverage on AGN. So I took the AGN catalog and colored it by objects with a number of visits greater than 250, 500, and 1,000. Okay, and there are a few areas of deep drilling fields with more than 1,000 observations, and so there's 76,000 AGN candidates with n greater than 250 and observations, 7,300 with n greater than 500, and 1,200 objects with n greater than 1,000. So that's a good data set to do things with. And the data is in principle public, but we keep discovering things every now and then. So the best way to get the data right now is to ask me, and then I will get you access to it. And I think Niel's not here today, but I have a student's going to look into verifying things in the deep drilling fields, and then I think we'll release everything off that Lucia Quest sees in the deep drilling fields, which should only be 100 gigabytes, so manageable, even on a Mac. And then you can play with it and see what's going on. So, and there are cool things in there. Here's a QPE, where if you Fourier transform the data, make a periodogram. This does not like a misphotometer, not look like a misphotometer galaxy. Looks like an AGN. So maybe we're picking up something, and curiously, the period finder used for stars found a period of 460 days, which is twice the one found in X-rays. Who knows? But it's cool. So there's a large data set that directly overlaps with LSST, sort of goes to Z of order 22, and can be used to find AGN, and contains lots of other interesting objects, some of which can contaminate AGN samples. So this is a good training set, besides ETF, to train things on and see how the contamination works. And when LSST turns on, I know this, it's going to be very hard to get lots of spectra for anything that can't be done with a 4 meter. And when you get to V of 22, you're sort of hitting several hours integration time on a 4 meter if you want good signal and noise. So the foremost survey will not integrate more than 2 hours. So basically, we have variability light information, light curve information for almost anything that has abundant spectroscopic coverage. So we should get started now doing this stuff. And we can do the same things with ZTF. And it'll be really cool to put ZTF and Lucia Quest and see what objects we don't identify and why in each other's surveys. Because AGN are kind of random, and sometimes they go dead and then they jump. So if you take a narrow slice, you may or may not pick it up. So we want to understand how big an effect that is. So I think we can get started now doing LSST science, and I'll do my best if anybody's interested to make the Lucia Quest data available. Thanks a lot. Okay.
Sorry.
Yeah, sorry. Go ahead.
Awesome. Thank you so much. We're actually a little over time, but we have the discussion at the end. So I think if you have any questions over Zoom, you can send a message over Slack or the Zoom chat, and we'll do some questions at the end. Yeah. Yep. So, all right, we'll move on. Okay, we have Meg Davis. You want to? I'm guessing that one's yours, but. I'm sorry, yeah. Okay. Perfect. Oh, yeah, don't worry about it. Let me just check this real quick. Okay. Yeah. We can roll over, yeah.
All right. Good morning. My name is Meg Davis. I'm a PhD candidate, 5th year at the University of Connecticut. I'm also an NSF Graduate Research Fellow there as well. I work with Jonathan Trump, no relation, particular emphasis on that this week, or next week. As well, I work also with some wonderful collaborators in the AGN Science collaboration and otherwise. Today I'm going to chat with you all about binary supermassive black hole detection with Rubin, some survey strategy requirements, light emphasis on requirements. We have some recommendations, rather, maybe, and also a bit of outlook for binary supermassive black hole detection. So first I'm going to take you on a quick crash course on the binary detection problem and what we're trying to do. So binary supermassive black holes form through galaxy mergers. Here on the left, I have examples of dual AGN, not gravitationally bound to each other yet, of varying degrees of nuclear separation. You can see those nuclei, those supermassive black holes that are actively accreting there quite well in those photos. We're talking kiloparsec to parsec scales. Through interactions with gas, dust, stars in those galaxies, and over millions, if not billions of years, they eventually make their way down to a gravitationally bound binary pair. For the binary detection problem, it's really important to note that when they're gravitationally bound to each other and are in this pair, they are likely to be surrounded by a circumbinary accretion disk. Each nuclei have maybe their own mini disk, and there should be streams from that circumbinary disk onto those mini disks. That'll be important to remember for later, and we're talking parsec to subparsec scales here. Finding them has broad implications for many areas of active research. I'm particularly excited about gravitational wave physics, as these objects may constitute the gravitational wave background, and also galaxy evolution, hierarchical structure formation, and I'm particularly fond of accretion, so there are consequences for accretion physics there as well. The issue is optically, photometrically, I'm going to repeat that because that's my niche, that's my area of expertise. Optically, photometrically, we have hundreds of candidates, but no full confirmation just yet. And I'm going to explain that now. I'm going to start with what we're looking for. What we're looking for are periodic signals, sustained periodic signals. Binary supermassive black holes can produce these periodic signals through Doppler boost. I have an asterisk there and more examples down in the bottom right-hand corner because in astrophysics, as most of us know, there are 1,000,001 ways to make a periodic signal. Same is true with binaries. But we typically roll with Doppler boost. Through Doppler boost, so these black holes are moving at significant fractions of the speed of light. In that orbital motion, we'll modulate a light curve. So we're looking for periodic light curves. The issue is that, again, remember that this binary pair is in a circumbinary accretion disk. There can be thermal fluctuations in that accretion disk that make some sort of optical variability itself, and that optical variability can also look periodic. So here I have examples of simulated light curves. On the left-hand side, we have a binary supermassive black hole simulated light curve. That there is indeed a periodic signal hidden within that noise. And that noise is also a signal for like single quasars where that's the natural optical variability highlighted on the right. If you maybe squint a little bit, maybe close one eye, you could curve fit these both with a really simple sign fit and get a decent chi-squared. I know because I've done it. So is there hope? That's my question I always like to ask, is there hope? And then I also quote The Sopranos and I say, hope comes in many forms, one of them being Rubin, why I'm talking to you all today. Rubin comes online in 2025, it's going to revolutionize astrophysics as we know it, and AGN science with Rubin is going to be pretty spectacular. Rubin's cadence, baseline, and expected AGN number density could help us solve our problem. If we do a quick back of the envelope calculation, assuming that we're maybe looking at quasars, so not all of that 20 to 100 million AGN, some subset of that, and then comparing to previous surveys with binary candidate number densities, maybe we could expect hundreds to thousands of binary candidates, which is pretty cool. Hopefully some of them are real. Also to note with Rubin, it's going to produce 20 terabytes of data every single night. Not all of those are going to be AGN. Shame, really, in my opinion. But once we triage to AGN, triage to quasars, triage to binary candidates, it's going to be a long process, and we're going to need some pretty fast, computationally inexpensive detection methods to triage first, and then move on to more in-depth analysis methods. The bulk of my thesis work was on computationally inexpensive detection methods to do some of that triage and predict what we're going to find with Rubin. So here are some examples of some of the light curves I've created, and an example of one of the binary detection methods I've developed with many others in the collaboration. In my first paper, which is highlighted here, and that's what the QR code is for, I created millions, about 4 million single and binary supermassive black hole Rubin light curves, a broad underlying parameter grid, and now get to test a bunch of detection methods. So yeah, like I said, highlighted here are curve fits. The top one is a single isolated quasar, the bottom is a binary, and to be quite honest with you, the top light curve looks like it could have some long period to it if you squint a little bit. Hilariously, the top curve has a better chi-squared, which is mind-boggling, but it's true because of the noise properties and the magnitudes on the y-axis. So we have millions of quasars and are testing multiple detection methods. I won't be getting into the direct results of these detection methods because what I actually wanted to present to you today is investigating how those results change as a function of survey design. So initially we were testing 5-year baseline light curves with a deep drilling field 1-day cadence. But now we want to see what happens as we change that cadence and that baseline. So unfortunately, if you missed my dissertation talk, you missed all the results of that initial paper. But please ask me questions. I like talking about it. So in this plot, I'm highlighting 4 different cadences for an I-band magnitude or I-band filter light curve. In the yellow, I don't think I can do it's really faint. The yellow is a deep drilling field cadence, so an effective 1-day cadence. Then we have wide, fast, deep, so that's the main survey, 3-day, 7-day, and 10-day effective cadences, all over 5-year increments of baselines. The 10 years of LSST, and then maybe extending the baseline either through Rubin or otherwise with other surveys, we wanted to explore that. We also explore host galaxy contamination, but I won't have a lot of time to highlight that, so I'm going to really not talk about any of that today. So it turns out, and this is rather unfortunate for a lot of the arguments needed to do, or that we're forming for AGN science in general, cadence doesn't matter. It matters a little bit. But it actually turns out that baseline, and that's a really small title at the top there, but it turns out that baseline matters way more for binary detection, initial binary detection, than cadence does. So on the left-hand side, we have false positive rate, so single quasars that trick us up and make us think that they're binaries. And on the right-hand side, we have recovery rate. We're looking at can we get out what we put in period-wise for that binary signal. And you can see tight clustering of the points. The different colors correspond to different cadences. And then a dramatic difference as we move across the baseline across that x-axis. The circles are uncontaminated, and I do have a couple of examples of contaminated results as well. But again, I don't have a lot of time to highlight that. So I'd also like to highlight Caitlin Witt is a collaborator of mine. In her 2022 paper, she also found that baseline extension positively impacts binary detection with a curve fit method. Her beautiful Bayesian curve fits are pretty fantastic. And I would also like to mention that Caitlin is on the job market. So if her application comes across your desk, you should hire her. Her work is quite nice. So it's a bit unfortunate that we don't have any cadence arguments to help you all out with your cadence arguments for getting that smaller cadence. But I promise there's hope. Like I said, this talk focuses on hope. We're also testing more complex methods. This is a depiction of new multi-band light curves. If you have more questions about those, I can get into that later. But we have multi-band color information coming down our pipelines now. And we get to now apply not only single-band periodograms, so Lomsdorgel periodograms, but also now combine all that color information for multi-band periodograms. Here, what is happening as we move through the animation is the cadence is changing, especially in that top plot there. You can see almost the thickness of the lines changing. And you can see, I'd especially like to highlight the multi-band periodogram, that there's some variance there. They look relatively all the same. Some cadences are indeed worse than others, but for the most part, they look quite similar. What happens when we change baseline, there's a bit more of a dramatic difference in what those periodograms look like, which is quite interesting. So in my opinion, I believe for detection, initial detection, longer baselines will increase detection potential more than any effective cadence will. So a reminder, I've said it a few times now, this work is focused on finding the binary supermassive black holes, not on what cool, amazing, wonderful science we can do with them yet. When we get to that point, once we actually find them, we're going to want to probe these objects and find out whatever we can about them. That's when cadence is going to matter. So I guess that's where we come in with small effective cadences for that argument. But for detection, we need long baselines. Initial machine learning tests, and then also simulations featuring like the accordion cadence of Bianco et al. 2022 are coming soon. I have a team of undergrads that I have the pleasure of working with who are working on that as we speak. Despite first light, we have time, right? We have a couple years before we can even really start making any guesses or anything like that. And triage and candidate lists, so we have time. One question I've been getting all conference is what is going to be the smoking gun? So we're going to talk about Outlook for just a second. And I need you all to like prepare yourselves because it's kind of disappointing. There isn't one. I should say there isn't just one. This is absolutely going to be a multi-wavelength, multi-messenger endeavor. We cannot do this alone, and we shouldn't. Rubin is absolutely going to help. The cadence, the baseline, we're going to have some exceptional data. And I'm really excited to dig into that. Like I said, it's just going to take some time. We're going to have some pretty good inklings, some pretty good candidates from Rubin that we'll get to check out. But we're not going to do this in a vacuum. And like I said, I don't do this in a vacuum either. If you'd like to join the Binary Light Curve Simulation Project, about 15 people, subgroup of a subgroup, please contact Il Yoon. Thanks.
Awesome. We do have time for a question. Yeah, why don't you go ahead, if you come up to the mic just so the people on Zoom can hear too.
Hello, this is Scott Noble from NASA Goddard. Great talk, really interesting work. What population did you investigate when you made your search?
Yeah.
Because if it's chirping, I would think that the cadence would have an effect. But
yeah, so in these initial searches, we are looking for Doppler boosted smooth signs. So those are the binary signals we're looking for. But we do also implement some different pulse shapes, so more sawtoothy behavior as well. With methods like Kerfit, it actually doesn't matter what the pulse shape looks like as long as it's periodic. The Kerfits can actually find it and recover that if it's a real binary. So that's what we're focused on there. But a lot of my collaborators, like Maria Carisi, they're focused on really modeling all those really other interesting chirps, stuff like that. And there should be some wonderful work from Maria's graduate student, Eden Davies, soon, very soon. There's some very beautiful curves. Quasar-wise, the newest, most of this work features the underlying parameter grid of quasar luminosity functions from like Hopkins et al. So yeah, what we expect to see with Rubin.
Do we want to take one more question? I think yeah, someone there, yeah.
Hi, Megan. So I have a question about your conclusion that cadence doesn't matter. I would assume it does not matter for a certain range or of longer periods. Is that true?
Yeah. Yeah, if the period is quite short, we're going to want to probe that, especially if our baseline is quite short, then cadence absolutely matters. It's like a Nyquist frequency kind of argument. As we want to do any interesting science other than just finding them, cadence is absolutely going to matter. If we ever wanted to even try like reverberation mapping these objects, we need an improved cadence. I have reverberation mapping like curves, which wants to see those too. Cadence does matter. It can make a little bit of a difference, but for our work, it turns out that baseline just matters a little bit more. I'm being a bit dramatic, a bit facetious if I say cadence doesn't matter.
Awesome. Our next presenter is on Zoom, so we're just waiting for him to share his screen, and hopefully we can get going.
Am I audible? Hello? Am I audible?
Just going to stay here for a minute to make sure it's working.
Hi. Can you hear me? Can you hear me?
All right, we can't hear him.
I can hear you. I'm connected online and I hear you fine.
As far as I know, it should be hooked up to the speaker. He had me hook in this aux cord so that it's
Am I audible now?
Yeah, he
Hello?
said he would just be out in the hall and he would be around for, oh, there he is. Yeah, the sound doesn't seem to be working from the speaker.
It's working for me online.
Yeah, it is working online, but
Sorry, we'll get going in a minute.
the on-site participants.
Yeah. It's not on his end because it's working for them.
Yeah. Hello. Can you hear me?
So you hear that?
Yeah.
So that means that the channel is open. So it's just that your computer isn't outputting enough.
Do you want to try saying something?
Am I audible now?
Yeah.
Let me make sure that Zoom is...
Sorry, everyone. Oh, yeah, maybe I need to change the Zoom settings so it's outputting to the...
So small. Yeah, if you want to open up Zoom, I don't know why it's compressed.
Because I think it's just in a different desktop. So yeah, so there, and then, right. Oh,
So go...
what is happening there? Sorry, everyone. Oh, hold on, let's just. Oh, because it looks like I'm
Just
sharing
don't
my
worry about
screen.
it. Don't worry about the video. Just go
Okay.
to
The
the audio and then
right.
select speaker,
Right.
headphones.
What should it be?
Well,
The speaker is correct, so. Yeah, look, oh, okay. I
So yeah, now can you hear me?
think. No, okay.
so it's coming through.
Yeah.
So
Yeah. Okay, can you try speaking again then?
Yes, yes. So now can you hear me?
Oh, yes, you hear him quietly, so let's just increase the volume. Why?
So, oh, sorry. From this side. If you want to go ahead and talk for us.
Yeah, am I audible now? Can you hear me?
We can, it's just very faint.
There is some echo. Hello.
We say the ABC.
There is some echo. Can you hear me now?
Is there a reason why this is happening?
Till
Did you, when you share your screen, it does, is there,
I have already shared my screen.
what?
I have already shared my screen. So can you see my screen? And also there is some echoes from the room.
Okay, all right, fix it, okay.
Yes. And can you hear me?
No. Unless that got changed, no.
There's one in the hall, might be. Is this one?
None of them are.
Okay,
I think it's moving on somebody else.
Should I start?
Like there's a loop that. Did you try leave the?
Okay. Do we want to try now?
Yes.
Can you?
Yes. So yeah. So am I audible now? Can you hear me? Can you hear me? Hello?
get started.
Okay, then I am starting. Good morning. I am Amit Kumar Mandal. I am a postdoctoral fellow from the Center for Theoretical Physics of the Polish Academy of Sciences, where I am collaborating with Professor Bhojanath Charni. Hello. Okay. The title of my talk is Determining the Hubble Constant through Continuum Time Delay Modeling using Disk Reprocessing and the FRADO model of DLR formation in NGC 5548. This research topic is being carried out by Vikram Jaiswal, who is a PhD student at CFT, and my other collaborators are mentioned here. Okay, so active galactic nuclei are among the most luminous objects in the universe. This is a schematic diagram of the central regions of AGN according to the unified model of AGN, and the typical sizes of the hello. Okay, and the typical sizes of the different components in the central parts are mentioned here, where the accretion disk size can range between 10 to 100 Rg, where Rg is the gravity. There is some echo from the room, and I am unable to. Okay. Okay, and the broad emission line region can range more than 1000 Rg. So from these size measurements, it is clear that the central regions of AGN are very compact. So naturally, the question is, can the central regions of AGN be resolved? It is difficult to resolve these regions using any current imaging technique, but there is an indirect method which can be used to probe these regions, which is known as the reverberation mapping or echo mapping technique, where time resolution can be swapped for the spatial resolution. So this method uses an intrinsic property of AGN, that is the flux variability property. AGN shows flux variations over the entire electromagnetic spectrum. So I am showing you light curves in different wavelengths for an AGN, specifically in X-ray, which is coming from the corona, UV continuum, which is coming from the accretion disk, H beta emission line, which is coming from the broad emission line region, and NIR continuum, which is coming from the torus. And you can see that they are showing correlated flux variations. Therefore, by finding the lag between the different light curves, it is possible to estimate the size of the different components using reverberation mapping. So this is the basic idea of reverberation mapping. And using reverberation mapping, specifically by finding the interband lags between different UV optical bands, it is possible to constrain the size of the accretion disk using continuum reverberation mapping. So I am showing you an example for the target NGC 5548. So this figure, the right panel, shows the light curves in different UV optical bands for NGC 5548, which is taken from Fastnavigator 2016. And you can see that this object is showing correlated flux variations in different UV optical bands. And then the interband time delays are plotted as a function of wavelength, which is known as the lag spectrum, which is shown in this figure. And according to the standard disk model, the interband time delays should increase with wavelength, which is slope beta 4/3. And you can see that the time delays are increasing with wavelength. And the size of the accretion disk can be obtained by fitting the time delays as a function of wavelength by using this equation, where the normalization constant τ0 can be used to find the accretion disk size at reference wavelength λ0, say at wavelength 2500 angstrom, which is parametrized by R2500. The accretion disk size, okay, according to the standard disk model, the accretion disk size at wavelength lambda is given by this equation. Then we compared the accretion disk size obtained from the observations that is from disk mapping fitting, and as a function of the disk size as expected from the standard disk model in this figure, where the y-axis represents the disk size obtained by fitting the lag spectrum, and the x-axis represents the disk size as expected from the standard disk model. And you can see that the observed disk size is larger, about 3 to 6 times larger than the expected values from the standard disk model, which also indicate a contamination from VLR diffuse emission. Also, microlensing study of gravitational lensed quasars revealed about 4 times larger disk size than the expected value of from a standard disk model. So all of these observations suggest that the continuum lags are contaminated by the outer region, specifically because of the scattering in VLR and because of VLR and also VLR emission lines. So to model the observed time delays, we have developed a model which considers both the disk reprocessing as well as the contamination from outer region, that is from VLR. So according to the lamppost model, a point-like source, which is known as corona, is producing X-ray, which irradiates the accretion disk, as you can see in the video, and produce flux at a radius r, which is given by this equation. So we are sending a very narrow pulse. We are sending a pulse of very narrow width, like a delta function, and which irradiates the accretion disk and generates a Planck function with temperature Tr, which is given by this equation. And we can then estimate the transfer function using that Planck function at wavelength lambda, which is given by this equation. So we have generated transfer function for different values of lambda using the input parameters which are given here. And the transfer function for different values of lambda are shown here. And you can see that the transfer functions becomes broadened as wavelength increases, which is expected because we should expect larger time delays obtained from the transfer function as wavelength increases. Also, the transfer functions are found to generate from a single point, which corresponds to the inner radius of the accretion disk, which has very high temperature and basically irradiates the accretion disks at all wavelengths. But the time delays obtained from this transfer function are found to be smaller than the observed time delays. So to match the observed time delays, we included contribution from outer region, that is from VLR. As the continuum travels through the VLR, it encounters scattering in the VLR, and because of this scattering, an extra time delay is introduced, and we consider the time delay, that extra contamination by the term FVLR, and also the emission lines are found to contribute to the time delays. So we have included emission line profile, which is computed using Claudio and is introduced by the term epsilon lambda. And to obtain the BLR transfer function, we used BLR modeling. So we used FRADO model for our purpose, which was also developed by our group. Then the total transfer function is obtained by using this equation, where both the disk reprocessing as well as the VLR contamination is included. FRADO model, which is known as the failed radiatively accelerated dusty outflow model, is used to obtain the cloud positions in the VLR for NGC 5548. And the cross-section of the cloud positions is shown in the left panel of this figure, in this figure. And we have used these cloud positions and an inclination angle of 40 degrees for NGC 5548 to obtain the VLR response function, which is shown in the right panel. And you can see that the VLR response function has two peaks. So one peak arising at smaller time delays is mainly because of the VLR clouds, which are in the same side of the observer, And another peak arising at a larger delay is because of the Biela clouds in the opposite direction of the observer. And also we included the emission line profile, which is computed using cloudy, which is shown in the bottom panel of this figure. Then we merged all these. Included this transfer function, which is mainly because of the disk reprocessing, together with the transfer function, which is coming from the BLR, and also the emission line profile by using this equation to obtain the total transfer function, which is shown in the middle panel of this figure. And the total transfer function has two peaks. So one peak arising at smaller delays, which is mainly because of the disk reprocessing, and another peak arising at as larger delays is mainly because of the BLR contamination. Then we estimated the time delays at different wavelength using this equation, and then we plotted our model recovered time delays as a function of wavelength in the observed lag spectrum, which is shown in the right panel of this figure, where the black points with error bars represent the observed time delays as a function of wavelength, whereas the red points represents the time delays when only disk reprocessing is considered, and the brown points represents the time delays which is obtained the model and which considers both the disk reprocessing as well as the BLR contamination. And our model time delays are almost consistent with the observed time delays. Now to estimate the Hubble constant, we simultaneously fitted the lag spectrum as well as the observed spectral energy distribution of NGC 5548 for different values of accretion rate, that is m dot, Eddington ratio, and also by varying the luminosity distance dl. And the best fit parameters are obtained using the chi-square minimization technique. So the top panels in the right hand figure represents the chi-square values in Eddington ratio space, and the bottom panel represents the chi-square values in luminosity distance space. And using chi-square minimization, the best fit value for luminosity distance is found to be 71.7 megaparsec. And using the source redshift, then we estimated the Hubble constant, which is found to be 69 kilometer per second per megaparsec, which is close to the value of 72 kilometer per second per megaparsec as prescribed by flat lambda CDM model. So this is an ongoing project, and here I have summarized the future possibilities which can be done using LSST data. So LSST is going to provide light curve data in 6 different optical bands, like UGRIZY in UGRIZY filters, and using the interband time delays using this light curves data, it is possible to find the size of the continuum emitting region using specifically for the deep drilling fields of LSST, which is expected to provide light curves data for about a few thousands of sources. And the expected cadence required for performing continuum reversion mapping and also BLR time lag recovery using the LSST photometric monitoring data. The details will be presented by Santrutto Panda during his talk. And we also found a strong correlation between the disk size with Asian luminosity, as well as we found a strong correlation between BLR size and disk size. And these relations are very important because they can be used as a single epoch black hole mass estimator. And using future LSST data, it is possible to better constrain these relationships over a large dynamic range, specifically for the high luminosity agents. And the details will be presented by Su Wang during his talk. And finally, we can apply our newly developed method, this method, to model the recovered time delays obtained from LSST by selecting suitable redshift range that covers the Bama range. Thank you.
Awesome. Okay, and I think the sound is all up and running now. So yeah, sorry for the delay, and thanks everyone for your patience. Yeah, I think we're gonna push the session back 15 minutes and just cut into the discussion time a little so everyone gets a chance. But we do have time for a question. Is there anyone in the room who has a question? I think we have a yeah. Yes, I think yeah, there's time for a question. So does anyone over Zoom or in the room have a question? Yeah, go ahead. Yes, if you can go up to the mic, yeah.
So I know, the group in which you collaborate has already provided some useful feedback on the suggested cadence for the deep drilling field. Based upon the work you've described here, and I guess the work to come by Dr. Panda, do you expect to have further important inputs into your suggested cadence for the deep drilling fields?
Yes.
Could you describe what that feedback is likely to be?
So actually, Shantanu Panda will discuss in detail. So exactly, I don't know currently what is the output. So he will discuss in detail about the cadence. So what is required for this performing continuum reverberation mapping?
Okay.
Yeah, he will discuss in detail.
Okay, thank you.
All right, Igor, I think you're next. So if we can swap shared screens.
Okay.
Yeah, if you want to share your screen.
Can you hear me?
We can hear you, yeah.
Okay.
We just don't see your screen yet. There we go.
Are you seeing the screen?
Yes, everything is all set. Why don't you take it away?
Okay, thank you. So, hi everyone, my name is Igor, and I'm a master's student at Federal University of Rio Grande do Sul in Brazil. And I've been working under the supervision of Thaisa Stark Bergman. And today I'll be presenting this work we have been developing in the last year, also in collaboration from Panda, which is going to give a presentation later on. And I highly recommend you all to watch this presentation. And in this work, our main goal was to study the inner structure of a quasar sample via photometric data from the LSST. And we aimed to explore the relationship between this variability, this photometric data, and fundamental properties of the sample, such as luminosities, azimuthal ratio, and black hole mass. And since we are really engaged to the LSST data, to the LSST project, we decided to go with the ZTF data to start our preparation for the future use of the LSST data. Also, in the second phase of this work, which is currently underway, we plan to calculate the time delay between photometric bands using cross-correlation techniques and derive the physical side of the accretion disk, and also look for correlations with that. Well, our sample is based on the all-quasar multi-epoch spectroscopy program with the ACMIS sample that is being monitored within the Black Hole Mapper project of the SDSS5. And more specifically, to the ACMIS median subsample, which has a reasonable number of sources and a higher cadence among all of the fields in the project. And specifically, also we selected quasars or sources that have declination below 30 degrees in order to use the same sample in the future for the LSST if we decide to. At the end, we got a total sample of 2,058 type 1 quasars, spanning a redshift range from 0 to 3. Here's an example showing the fields. So in red, we have the chosen one, the ACMIS median. As you can see, it has a reasonable number of points and also a higher cadence. The ZTF or Zwick Transition Facility, I'm not going to talk much about it, but you may already know the ZTF. But it's a survey that explores the transient sky, and it scans the entire northern sky from the Palomar every 2 days using its three filters, ZTF, G, R, and I. But unfortunately for this work, we couldn't use the ZTF I band. And we also decided to use the forced photometry service from ZTF, as it uses the point spread function of the observation as the aperture for the forced photometry. Here are some SDS spectra from our quasar sample. And as you can see, they have different, also with the ZTF filter transmissions highlight overlapped. And as you can see, they have different redshifts, and that's because we did calculated the different contributions from those emission lines within each redshift being, and also each ZTF filter. And on the work, we did a more detailed approach. We had like 5 or 7 beams, redshift beams. So just to make sure that the variability we were seeing from the light curve weren't contaminated with emission lines contribution. And we did not find a significant line that could be interfering in the purpose of this work, which is to analyze the overall variability in the 6 years light curve from the Also, once we got the ZTF, the forced photometry data, we had to process and to filter out the light curves to make sure that they were reliable and useful. And for that purpose, we developed this custom Python code, which is openly accessible through this GitHub. And basically, what it does, I'm not going into much details here, but we remove not available values, which are the upper limits in the light curve. We also resample same-day observations by their mean, and we calculated this 30-day rolling average flux and root mean square to filter out that deviate more than 4 times the root mean square. After that, we also look for light curves with length, like we only keep it data that has more than 100 observations per light curve. And after that, we get a final light curve that we use it for cross correlation techniques and also to obtain the variability. And after all this process, I didn't put here, but we got 915 sources in the final sample. Here on the left, we have the older version of the code where we were using magnitude instead of flux, and our variability parameter was the RMS. And also, as you can see, some outliers weren't being removing by the older approach, and some useless light curves were going into the final data. With this new approach on the right, we have the flux instead of magnitude, and as you can see, we have a much cleaner light curve. Well, the mean fractional variation, or the FVAR, which is our new approach, basically it accounts for adjusted the observation uncertainties. Is basically the root mean deviation adjusted for the observation uncertainties and divided by the mean flux of the light curve, which ensures us that we are not biased by uncertainties and distance effects as well. That's the idea behind this new approach. Well, once we already everything defined, we just need to put in histograms, and here we have the G band, R band histograms for the 4 different redshift things. As you can see, the G band has a higher number of source, and variability, a higher variability as well. Is that what we should expect from when looking to AGNs, the wavelength varying? And for that reason, we decided to take the G-band as the reference, as our reference variability. And of course, we divided into 4 redshift beams to see how the relations will vary across cosmic time. Well, and now we go to the characterization of the sample. We performed a cross match with the SDSX DR16 Fraser catalog. And here are some properties highlighted. We have the black hole mass, the volumetric luminosity, the black hole mass, and the Eddington ratio. For the histograms for the filtered sample, as well as the absolute magnitude in the G-band and the redshift distribution for the filtered sample. And well, we already got the 2 main things we needed to achieve the main goal of this work, and we just need to put them all together. Here are the black hole mass against the FVAR, both in log space, colored by, on the left, sorry, colored by the redshift. And as you can see, it seems to have a segregation with redshift. And when you go to redshift beams on the right, you see this segregation. And what is interesting here, we also calculated the Pearson coefficient, correlation coefficient and the p-value, where the null hypothesis is no correlation between the 2 parameters. And as you can see, on the lowest redshift beams, it appears to have a weak positive relation, which have been found on the previous works on the literature, as well as a weak negative correlation at higher redshift beams, which has already been found by some works, previous work. Wow, and the main debate, I think, which is the relation between Eddington ratio and FVAR, of course, both in log space. We don't see a segregation, we didn't see a segregation with the redshift. And when you go to the redshift beams and the regression lines, I didn't mention that we are considering, with that regression line, we are considering the uncertainties within each point. So, and we see a constant anti-correlation between those 2 parameters. And for that reason, we defined the all points regression line to try to achieve a linear equation between those 2 parameters and see how well this relation is predicting the results we find. Of course, they are linear in the log space. And here, to give a bigger emphasis to the overall regression line, and also, we did this CI and CI plot in the shaded red and green region, the confidence interval and the prediction interval, and as you can see, for the overall regression, and as you can see, we can the data lays between those intervals, which really excited us. I think that's okay. I didn't mention, but we also looked for another correlations within the continuum luminosities and the FVAR, and also the volumetric luminosities. And we find a persistent anti-correlation between those parameters, which we expected. And for the O3 emission line as well, we find no correlation at all. And it's also what we expected, since the O3 is from the narrow line region, and we shouldn't be able to see any bigger variability in 60 years observation period, which is the light curve, which is the LITF light curve length. And also, as I mentioned, the relationship between black hole mass and FVAR shifted from a weak positive correlation at low redshift to a robust anti-correlation at high redshift. And of course, a persistently negative correlation exists between the identity ratio and the F bar across all redshifts, with the strongest correlation at the lowest redshift bin. And using the entire sample, we could achieve a linear equation, amount space, and we think it has a high significance for future AGN variability studies. And of course, we hope to improve all of this work when the LSST data is available in the future. Thank you all. I'm glad to answer any questions.
Awesome. Thank you so much. Do we have any questions in the room or over Zoom? Time for a quick question. Okay, I'll ask one. Can you speculate on why you think maybe the mass and the variability are anti-correlated and why that actually changes as you go to higher redshift? Do you have any thoughts on why that is?
Yeah, actually, on the last year, I was in the LSST La Serena meeting, and I saw some results that were comparable, I think from Arevalo et al. And she was investigating the variability, the different time scales from variability. It may influence or not the correlation obtained from the black hole mass and the photometric variability. But to be fair, I don't actually know exactly what would be interfering in those relations.
I see. So you're saying because the time scale, the variability gets redshifted to essentially you're looking at shorter time scales as you go to higher redshifts, the impact of the mass is different at these different time scales. That makes some sense to me. So
Yeah.
That's interesting. Awesome. Okay, we'll move on to the next talk. I think we have Luis up next. So if you want to share your screen.
Yes. You can see my screen?
Yep, you look and sound good. So take it away.
Okay, so good afternoon, everyone. My name is Luis Mateus Dourado Sanches. I'm from Federal University of Rio Grande do Sul in Brazil. It's a pleasure to be here today presenting my work. My advisor and co-author on this project is Thaisa Stork-Bergman, and the title of my presentation is Optical Variability Analysis of Low Redshift Quasars with the ZTF and Future Prospects for the LSST. So, thank you all for your attention, and let's get started. So the primary goal on this work is to investigate the luminosity variability of the quasars and how it correlates with the physical and spectral properties in the AGN. The other goal is to identify quasars with a broad double-peaked profiles in the spectra and investigate if these objects show us distinct variability relationships with AGN properties. We also want to perform cross-correlation analysis of light curves obtained in the G, R, and Y bands, using the time delay between these bands to gain a deeper understanding of the structure and dynamics of the accretion disk. We are also using the ZTF data to prepare for the LSST data in the future. And so far, we have analyzed the variability in amplitude, but now we are interested in examining variability over time too. So our data was taken from the ZTF, that is a public-private partnership that uses the Samuel Oshing telescope on Palomar Observatory. with a wide field camera that scans the entire northern sky every 2 days in 3 filters. These 3 filters are G, R, and Y band. So we utilized the ZTF data to plot light curves and calculate the variability of the quasars on a time scale of almost 5 years. So in the future, you can do shorter time scales too. Our sample was drawn from the catalog by like and filtered for this little range of redshift here. This range of redshift was chosen for 2 reasons. We want to minimize the effects of the redshift and ensure that observations have H alpha and H beta on the spectra. To ensure a higher reliability in the analysis, we selected data with a good number of nights, so observed nights, so more than 100. And it reduced our sample to 472 objects. And well, the last thing, we visually selected objects with double-peaked profile in H alpha and H beta from the SSD spectra. Here we have some examples of a spectrum with a double peak profile. Here is a candidate to double peak profile. Here has a spectrum with no double peak profile. The initial motivation to separate the sample in double peak and no double peak profile was test the hypothesis that double peak profile quasars could be more highly variable sources. So here are some histograms illustrating the difference or similarity about the 2 samples. We can see that double peaked quasars are more massive than no double peaked quasars. So in bolometric luminosity, is a similar for the both samples. And because of these 2 facts here, we can also see a lower Eddington ratio for double peaked quasars. And last 2 histograms here, we can see that the luminosity of forbidden O3 and the variability are slightly higher for double peaked quasars, but not too higher than the mass. Our methodology that we utilized on this research, first of all, we used the forced photometry data from the ZTF to obtain the light curves. With the light curves, we could calculate the FVAR. So the FVAR measures the intrinsic variability of a source by quantifying how much it varies relative to its average brightness. And with FVAR, we could investigate the relationship between AGN properties and the variability. So we use the data from the catalog by Yu and Shen and performed a linear regression between FVAR and these properties that we catch from the catalog. So for the future, we plan to use tools such as Pyroa and Javelin to calculate the delay between photometric bands, and this will allow us to estimate the size and other characteristics of the accretion disks. So here represents some examples of the light curves that we analyzed. So these light curves were used to calculate the FVAR and will be later, or you will use it later to construct the reverberation mapping. So we have an example for low variability, medium variability, and high variability. So since we had more data from the G band, we chose this band as a reference to our FVAR analysis. So when in the next slides, when I say FVAR, I will be saying about FVAR on G band. So in this section, I present the relationship between physical properties of the quasars and the FVAR. So for mass of the black hole and luminosity of forbidden O3, we can see no correlation with the FVAR here in the separate samples, double peak and no double peak. But in bolometric luminosity and Eddington ratio, we can see there is an anticorrelation with the FVAR, and this anticorrelation is stronger for the sample with no double peak in the spectrum, in the both. So we also analyzed several spectral features obtained from the catalog by Yuan Shen, and he represents some results of full width at half maximum of some emissions. We catch forbidden O3 emission to represent the narrow line region, and H beta, H alpha, H beta, and MG2 to represent the broad line region. We can see in this first plot here anti-correlation with the FVAR. But this anti-correlation is only stronger for our sample with no double-peaked quasars. And here in the broadline emissions, we can see that for double-peaked quasars, the line of emission, the full width of emission is broader, so they are in a higher place in all plots of the broadline region. And weak correlation with the FVAR here, but just for double-peaked quasars. With no double-peaked quasars, there's no correlation. We have also calculated the spectral slope between this interval here and compared its value with the FVAR. So here in this plot, where we can see that quasars with a steeper spectral slope tend to be more variable, even though this correlation is not that strong. So since our goal is analyze the accretion disk, we primarily focused on the continuum of the spectra. So we need to be cautious about how emissions might contaminate our analysis. And we observed that overall average contamination from the broadline region in our sample is very low. Here is an average for G band, R band, and Y band. And for our objectives, the maximum contamination for each band is shown here too. So even though this 8% here might influence in variability in our reference band, it does not significantly affect the FVAR value. Will be not. So what I want to say is that for now, it does not interfere in our analysis. But in the future, when we aim to reproduce a reverberation mapping, we need to be more cautious because we will influence. So the conclusions here is things that I have already said. So it's just here to reverse. So let's minimize this. Okay. And we could see that in double-peaked quasars, we have a higher mass of the black hole, lower Eddington ratio, a higher luminosity for forbidden O3 lines, a broader emission lines in the broadline region, and that double-peaked quasars tend to have a higher variability. We also see that no type of sample double-peaked or no double-peaked in our research shows any significant correlation with the supermassive black hole mass. We also see that for bolometric luminosity and Eddington ratio, we find an anti-correlation with FVAR, but this anti-correlation is stronger for non-double-peaked quasars. So, other thing it's important to say, it's the quasars with a steeper spectral slope tend to be more variable, but this correlation, as I said, is not that strong. So it's not definitive. And the physical reasons for all this behavior are still under discussion, and we plan to do the explanation for this on the paper or in a future presentation. As I said, this work is ongoing. Once we have the complete analysis, we will have more robust conclusions to present to you. So I don't think we have so much time. Here is a slide of how LSST would improve our research. So with the more filters, we can study the accretion disk more deeper, and with a high photometric, we can also find AGNs weaker with a low luminosity. So I would thank CAPS for funding my scholarship, and I would thank to Panda for always being so helpful with us. So if we have time and anyone have any question, I can answer now.
Awesome. All right. Thank you so much. Maybe a really quick question from Niel at the microphone. Sorry for making you get up.
So my question was a bit on that point you mentioned near the end about the physical interpretation. How do you plan to make a physical interpretation? One thing I might try would be to try to go and get spectral energy distributions, for the double peak sample and for the non-double peak sample, and to look for any systematic differences, because of course the ionizing continuum there is what's responsible for making the emission lines where you see these different correlations. Is that something you're planning to try, or what is your strategy toward getting a physical interpretation of all of this?
So I plan to discuss with Thaisa how can I explain this? So I would discuss what's the characteristic we are observing significs in physical. I don't know how to explain, but double
Okay, well,
Yeah.
no problem. One suggestion, which I hope might be useful to you, would be to look at the spectral energy distributions of the objects in your sample, because of course the ionizing continuum that's measured there is what's responsible for making the emission lines that you're measuring. So give that a try and try out other things as well.
Okay.
Awesome, great. And we can talk about this a little more. We'll have a little time for discussion at the end. So why don't we get the next speaker, Shu? So if you could, stop screen.
Yep.
Awesome.
So is my voice clear?
Yes, you're all set. So go ahead.
Okay. So hello everyone. My name is Shu Wang. I'm a postdoc from Seoul National University. And today I'm very honored to have this chance to present my recent work. And the title of my talk is estimating the AGN black hole masses via the continuum regression mapping in the error of LSST. So let's start. Yeah, so RM is a very effective technique to trace the inner structure in AGNs. Like for example, we can use the optical to UV lag to constrain the disk sizes. We can use the lag between optical to infrared to measure the size of dusty torus. Also, the lag of broad emission line relatively to the optical continuum is often used as the tracer to the broad region sizes and then the black hole mass estimation. But today I will focus on the continuum reverse mapping. So the variation of the UV to optical wavelengths is typically assumed to be caused by the reprocessing of the X-ray emission from the corona. So the higher energy emission from the inner part of the disk will lead to a lower energy emission from the outer part of the accretion disk. So we kind of expect that the lag will increase it with wavelengths. So this is kind of what we observed here. And let me briefly summary what is the previous findings in this kind of continuum RM studies. Like there are several local agents with intensive UV to optical monitoring. Like NGC 5548 is one of the best example. And the standard thin disk model actually predicts that the lag wavelength relation have a Paolo index of 4/3, which is consistent with our observation. And however, given the black hole mass and the Adin ratio derived from the emission line RM observations, the observed disk sizes are typically too large compared to the prediction from standard thin disk model. So as shown here in the example of NGC 5548, which has a typical Adin ratio of close to or lower than 0.1. So the observed lag wavelength relation tells you the disk size is about 3 times larger. In addition to this, you can see the lag excess in U band, which corresponds to the wavelength of the Balmer limit. These two important observational signatures actually are typically found in local AGNs. Like here, like I made a summary of the ratio between the observed disk sizes relatively to the standard disk model prediction for the local AGNs. You can see the ratio is typically ranges from a factor of several, like 3. And in addition to this, you can see in these 4 examples, the U-band excess is often, but not all, observed in the local AGNs. So what kind of mechanism actually give rise to such observational signatures? It is still under debate, but one of the leading scenarios is the contribution from the region diffuse continuum. And physically, this diffuse continuum can come from the bound-free, free continua, or scattering of the incident continuum in the brine region. So according to the radiation pressure confined model proposed and illustrated by Nether et al., and the fraction of the Brane diffuse continuum in the optical wavelength region ranges from like 20% to 40%, depending on the wavelength. And in specific wavelengths, such as like Balmer limit, you can see the excess in the fraction of the diffuse continuum contribution. So using this model, Nether successfully modeled the observed lag with relation for a sample of local agents. So suggesting that these two observation signatures can be resulted from the contribution of broad region diffuse continuum. Also, I want to mention another important evidence from the frequency resolved lags, where people can isolate the slowly varying signals and the fastly varying signals to measure the lag within these signals. They found that the slowly varying signals can reproduce the lag of the broad regions. And so another important effect may come from the continuum R relation. So actually, in the local agent sample, many of them have both the H-beta lag and the continuum lag available. You can find in the red upper figure that there seems to be a continuum R relation, just as the Bollinger R relation. So in the left table, I just made a summary of the ratio with lag and continuum lag in the several local agents. So you can see the ratio is typically a factor of few, like 5, ranging from 5 to 8. It doesn't seem to depend on luminosity, and this average ratio is not far from the prediction by the radiation pressure confined model. And so then after that, actually there are several progress. First is that the people have successfully measured the disk sizes in one of the most compelling SMBH candidates, NGC 4395. It shows a similar disk size problem to that of higher luminosity agents. And if you put the NGC 4395 on the plane of the RL continuum RL relation, you can find that it follows the relation quite well, and suggesting that maybe there is a common mechanism in here, both the SMBH regime and the supermassive holes. So the next progress is we have to test whether the observed tension is also observed in the general agent populations. So actually the local agents they most have the space and ground-based coordinate observations, which cannot be applied to a large agent sample. But thanks to the new generation of time domain surveys, for example, ZTF, we have multiple bands, good light curves for a large area of sky area. So me and my collaborator successfully measured a sample of successfully measured the disk size for more than 400 AGNs out to a redshift of 0.8. We still have the H beta covered to for the purpose of comparison with this model prediction. So you can see the typical light curve of an AGN with G-band magnitude of 70.0 at redshift 0.226, and we measure the GR and GI lag measurement used based on different methods and plot the lag wavelength relation. The conclusion is that we confirm the larger than predict problem holds for general agent population. And on average, this ratio is about three times. And this result holds when we restrict to a subsample with higher lag quality, the core sample. And so starting from here, we focus on the subsample with both the broad region size and the continuum emitting region size available. So in our paper, we found 21 of such objects, combining our DTF sample and the local AGN sample. So you can see here a comparable broad region and continuum R relation presented. They show a similar slope. And interestingly, the NGC 4395 is showing offset, and offset is seems to be consistent in both relation. And so this result, yeah. If next we want to make a direct comparison of the two sizes. So here, we just plot the primary size as a function of the continuum emitting region sizes, and feed it with a linear relation. And the result tells you that the observer's disk sizes at 5100 angstroms are about 1/8 of the primary sizes. And the best fit relation gives you a slope that is consistent or slightly shallower than 1.0, and with no large intrinsic scattering, which is 0.28 dex. This ratio actually is consistent with what we mentioned, the prediction from the RPC model 8.7. And this ratio, together with intrinsic scatter, may have some implications on the black hole mass estimation. And first is that, the traditional emission line RM, we have to assume the continuum region size is negligible compared to that of the broad region. So, however, I just discussed that the continuum emitting region is 1/8 of the broad region sizes, meaning that this assumption is no longer valid. For example, if you measure the lag between H beta and the 5100 astro, you are underestimating the true broad region sizes by a factor of 12%. And this also makes the RM-based black hole masses slightly underestimated. And this is first implication. The second implication is that based on this relation, so we can try to estimate the black hole mass using the continuum RM by replacing the broad region sizes in this visual equation with the continuum emitting region sizes and adding an additional parameter. So we apply this, we derive our relation and apply the relation to the rest of our sample. So for the best light qualities core sample, it shows very consistent black mass between each other. And I think this approach is potentially very efficient especially for heavy AGNs. For example, if you want to have the black mass direct black hole mass estimation for our redshift of 2 AGN, your emission line at the observed frame will more than 1 year or several years. So that means you typically have at least 3 years 3-year baseline to have a robust lag detection. While the continuum is on the order of months, if you are lucky that you have captured very good variability features, that you can have this lag measurement within 1 year. Okay, so I would like to talk about some ongoing efforts and future prospect. And I think this relation still needs to be validated more. First is the sample is still small, and there's the the dynamic range in the ratio in the luminosity is both limited. And we have to connect between the supermassive hole and the SMBH regime. And to do this, we can rely on the sample with both the spectroscopic RM and continuum RM. There are several ongoing efforts from our group. First is that the SNU AGN monitoring project, which focus on 32 higher luminosity AGN quasars. We have also have B and V band photometric light curves with cadence of 3 days or 5 days. So when combined with GRI band from TTF, then we can have 5 bands to constrain the light valence relation. And we have finished this work by and submitted, and you can see the result of our sample, just consistent with the previous work. Then and the updated relation is consistent with the previous relation. And second is that
I'm sorry to interrupt. We just try and wrap it up because I want to make sure everyone has time to talk and we're getting to the end. So.
Also, we are ending.
Sorry, yeah, we're just at time. So if you just want to make your final point, yeah.
Okay, thanks. Okay, so CAMP is going to fill up the intermediate Seyfert regime with BVRI. So so I have no time to talk about MBH regime, but we are still working on it. And several progress have been published. And okay, so like I said, CTF we only have limited cadence and limited number of bands. So this kind of the limitation of our work, which can be improved by the LST. So again, I just want to finish with one sentence that the spectroscopic and the continuum RM in the deep Gillian fields may provide a test bed for this relation. And if it's confirmed, we can extend to hazy AGNs in the future. Thank you. That's all.
Awesome. Thank you so much. Sorry about that. Yeah, we can give some applause. Awesome. Okay, we'll defer any questions. We might have 5 minutes for discussion at the end. But why don't you unshare your screen, and Panda, if you want to share your screen so you can.
I'll go ahead and share my screen.
Yeah, I am, it's almost irrelevant at this point, but I am sending 5 and 1 minute warnings over the chat for people in Zoom. So if you see your Zoom pop up, it probably is a 5 or a 1 minute warning. So.
All right. Yep. I'll just sharing it again. Something happened up there. Oops. I lost my screen over here. Just give me a second. Sorry.
No, it's okay.
Can you see my screen right now?
No, sorry.
Oh, not yet. Okay. Yeah. Something just happened. Let me try again. Amy, I would just like a confirmation once I put it on the full screen. If you do see my screen.
So we saw it, but now we're getting your presenter notes, not your
yep.
slides.
Okay. Yeah, that's. Let me just maybe put first that. So when I stop sharing, it just goes away. So and
yes.
That's me again. So. Yeah, well, anyways, I will. Let me see if this works this time. Still the presenter mode, I guess? Or
yep.
It's working now?
We're all good.
Okay, perfect. Thank you. Thank you
so
much. Sorry, everyone, for that brief fiasco. First of all, I'd like to thank everyone for giving me this opportunity to our group to present these works that we have been doing for the last couple of years. And I'd like to take a brief opportunity to all my previous speakers, especially Amit, Igor, Luis, and Shu, who have kind of laid the test bed for the talk that I'm going to give here. And I'm pretty sure that people are anticipating a lot of information from this one. So let me take it right away. So the talk that I'm going to focus today is about continuum and BLR time lag recovery. Initially, it started off as a part of the Polish in-kind contribution. We have geared up a lot of during this years, and now I'm going to show you some brief results that we have done with the version 4.0 cadence simulations, which supposedly should be the final one, hopefully. This is work in collaboration with my PhD supervisor, Bożena Czerny from CFT Poland, and Francisco Pozo Nunez from Heidelberg, Germany, and many other collaborators, including Amit and Igor and Thaisa group as well. So I will not take a lot of time on sort of recapping things that I've been talking about in the last few years, but here it's an LSST meeting. I just wanted to throw in some very recent pictures of LSST and the Rubin Observatory that I managed to go up to the summit as part of my on-duty work as a Gemini fellow. So it's a very cute little picture and such a nice landscape to really see all the telescopes sort of in the same site. So this is from a vantage point 14 kilometers from the summit, and gives you a very good idea about how many information and instruments that we are kind of working together under the NOIR lab scheme. So photometric reverberation mapping with Rubin. This is sort of giving you a glimpse of the idea that we're going to be enabled using the LSST over the 10 years period, and just giving an idea how different redshifts would be captured by the 6 photometric channels of LSST, and how we can use this information to ingest into our pipeline in order to get success rates for lag recovery, for BLR measurements, as well as for the continuum reverberation. So just a brief recap of what we have been able to do up to the point. Right now we have a pipeline that is fully functional, also being shared to the LSST collaboration. It's on GitHub. You're free to ask me if you want the link. I could share it again. And this is a pipeline for time delay measurements. So to the point right now, it is used as a prediction algorithm. But when the real data comes in, it is a dual purpose algorithm which can really be investigated with the real data of LSST. And the idea here is that we are sort of monitoring the emission line as well as BLR lags and continuum lags for any quasar that will be predicted by the Rubin Observatory using the latest suite of cadence simulations. So up to the point, we have been really testing this code with our real data that we are kind of combining from our 14 up to right now 15 years of salt monitoring of 3 magnesium-2 based reverberation mapped quasars, and many other instruments that have been actually encapsulated during this sort of multi-instrument reverberation mapping campaign that is led by Bożena since 15 years right now. With that, we are actually kind of benchmarking our code to estimate the time lag measurements, and the code is very modular. It allows you to include your own specific lag measurement algorithms. So it's kind of a free-flowing code in that manner. And this allows also to include efficient analysis by accounting for contaminations from the starlight and other emission lines, as well as I will going to show you, the diffuse continuum emission from the AGN. We also incorporate very realistic distribution of widths for realistic black hole masses and line widths that's coming right now from this SDSS. In future, the plan is also to include DESI, that's soon to be out with its data release, year 1 data release. And the idea eventually is to improve the predictive quality as well as testing on the DDFs that we have been already doing for the couple of years. So this is just the brief outline of how we are producing the mock light curves. This is something a lot of you have already seen. We're just making sure that we're taking the entire campaign duration, the most up-to-date cadence simulations, and including all the realistic effects that we can get from the spectroscopic catalogs. Here we are using the SDSS quasar catalog, DR16 and 18 right now. And eventually, the idea is to include as much as information from a realistic AGN, so contaminations from all starlight and emission lines, as well as including that in our power spectral distribution dependent light curve simulation, and basically in order to incorporate the red noise characteristics of quasars. We are testing over pairs of channel, and the code right now is sort of almost done for the 6-band channel and variable time contribution. And as I said, it's a modular code, and we can be using a lot of different lag methodologies to incorporate in our code. Just to give you a sort of, again, a brief idea how the DDFs look like and how's the extraction of the cadence simulations from it. And these are some representative baseline light curves, so to say, for the 10-year campaign from a little bit older simulation, version 3.4. I'm going to show you something about in the 4.0 simulations very soon. So briefly touching base upon our last work that we managed to do that with a lot of members of the collaborations who participated in this publication was predicting the BLI time lag and really envisioning the success rate over a long range of redshift and various luminosities and accounting for different cadence simulations back in 2022. The paper was published in 23, but back then we were using the version 3.0 cadence simulations, variety of them. Eventually, what is the idea here are the snapshots that you can see are for the 10 years and the 2-year campaign, 10 years on the left and the 2 years on the right, where you can see that the faint, we are considering faint AGNs as well as bright AGN characteristic representative cases. And eventually, the idea is, are we able to recover the lags as requested by the radius luminosity relationship? To an order, we were doing really good, especially when we are going into the full 10-year campaign. Both bright and faint AGNs do end up giving very good recovery, while, of course, maintaining the very large error bars. While in the 2-year campaign, in the early science cases, we might be doing a not so bad job when we are doing it with the faint AGNs. But it was always being underperforming based on the cadence simulations from back in 2022. So this is kind of the overall summary for this kind of the work that we did. Eventually, that we investigated different seasonal cases as well and requested a lot of different cadence from the main survey as well as the DDF survey and tried to look into all of the DDF fields with that version of simulation, version 3.0. And eventually, we derived out what was the best fitted strategy. Turns out the accordion cadence back then really worked out really in our favor. Still not matching the expectation, but was something that we would have actually predicted, as Niel pointed out. So this was kind of our prediction going forward, that it should be something like an accordion's cadence suitable for cadences for continuum lag recovery. Okay, so where are we right now? A couple of months ago, we got the version 4.0, the committee's survey cadence optimization committee's phase 3 recommendation. Seemingly, this is the final recommendation, if my understanding is correct. And there are 4 runs that were incorporated in this. I'm just briefly going over them. The 4th cycle basically is the idea that there are 2 regions of rolling strategies which can be implemented with up to 4 rolling cycles. This will be sort of starting in year 2 and ends in year 10. The baseline strategy right now includes a lot of TOOs opportunity. More of the order of 85% of this TOO time is going to be dedicated towards gravitational wave follow-ups. And rest are going to be for potentially hazardous asteroids and other things, eventually taking up to 3 to 4% of the total survey time to this TOO. And this is very interesting when I'm going to show you in the next slide the overall time recovery and the cadences. And there is another prospect of the one snap, really going back to the 30-second exposures with the U-band. And this is also another possibility that has been there, and we're testing that as well in our simulations. So just before going to the big reveal, these are some statistical trends comparing the version 3.0, 3.4 that we later used, and the version 4.0 that I'm going to show you right now. So eventually, the biggest change that we are seeing is basically happening in the Z-band and Y-band performance. So the number of visits has sort of kind of catapulted in the Y-band, and eventually it affects the Z-band sort of visits sort of to balance out the total filter balance. And another thing what's interesting is the result of this kind of balancing strategy on the mean cadence that we can really see on, in the Z and Y band. Effectively, they are counterbalancing each other. And the problem that we are going to face as well with the U band not being that much recovered. The last statistics trend that basically I've been searching is the minimum separation, which is pretty much equivalent to the median separations, especially for the DDF. Is that they are not really considerably different. It's basically the visit site of 30-second exposures. That's kind of also including the overheads of about 8 seconds, so 38 seconds overall. And in the max separations, we are seeing just a bit of variability effect in the U-band performance. So we are kind of getting a little bit more gaps of the order of 210 days in the U-band. So big question, did the BLR recovery get better with the version 4 simulation? Generally speaking, yes, it did get better. So here are the ones that are sort of shown in white are the new set of simulations that actually did the same repeat, but using the version 4 baseline strategy. And in both 2 years and 10 years, we do see a marked improvement. So the big takeaway here is the lag recovery in the fainter EGNs in the 2-year baseline really got improved. So this is a very good news for early science with Rubin, especially also talking about BLRs. And the overall success rate, however, underperforms in the new 10-year baseline. So especially as we are seeing in the one in the right side, for the redshift range between 1.7 and 2.6, this is the one I'm highlighting over here. This is where the part of the Lyman alpha enters the U band, while in 2.5, this is the part where the magnesium 2 is going to exit the Y band. And this is very kind of tricky, and we are trying to sort of look into it in more detail. But if you look at specifically the low Z, low luminosity, and high Z, high luminosity end, the recovery rates are much better than what we predicted with the 2-year back cadence simulations. Moving on towards a little bit of discussions toward the continuum reverberation mapping. As Amit briefly highlighted, the idea here is that we are trying to get prepare a comprehensive simulation that not only includes the accretion disk and the emission line, but also includes starlight contamination and diffused emission contamination from that, scattered emission. And incorporating all of that in our Gaussian process-based probabilistic cross-correlation method, which allows for modular priors, we are able to sort of do some prediction based on our current cadence strategies. This was a work led by Francisco Pouso Nunes, our close collaborator, and that led us to sort of write the research note a year later using the version 3.4 cadence simulations, where we found out that with that strategy and cadence strategy, the lag recovery were not that bad, especially at the higher mass range, about 10 to the power 8, 10 to the power 9 solar mass black holes. But really expecting anything for masses like 5, 10 to the power 7 or lower was really requesting a lot, and that was not predicted by the cadence strategy back then. And in order to really get good lags, and with that cadence strategy, we were also getting problematic information from the uncertainties, which were quite large associated with these lags, interband lags, up to 10 to 20%. So what improved when we used the version 4.0? So that's kind of a big slide. I'll just spend a minute over here on this. So this is a test that we have done, and I'm showing only for the entire 10-year lag. We are right now working on the seasonal versions of it to see whether really each season really lets us reveal the same kind of statistics that we are expecting from the version 4, which is kind of an improvement over the 3.4 simulation. So for the low mass case, which was a problem before, we do not really see a significant difference. However, there is slight improvement, especially when we are going towards the longer wavelengths. In the case 2, which is 510 to the power 7 black hole mass, intermediate redshifts, the Z-band uncertainty is reduced below 50%, and that's a substantial improvement of over 170%. That's a really big improvement there. Now, going towards the larger black hole masses, which were really doing not so bad previously, the uncertainties right now are below 30% and reaching as low as 20% in the I, Z, and Y longer wavelength bands. And the best result is with Z-band with 19% uncertainty, and that's a significant improvement, about 60% that we reported previously. And for the final case, the really massive black holes, the uncertainties are around 20% in the Z-band and stretching towards lower uncertainties about 11%. So effectively, if I want to summarize in one statement, the new baseline strategies for the version 4.0 have led to considerable improvements in the accretion disk time lag estimates in the DDF fields. And this is a test case with Elias, and we are going to show up and preparing a paper with all the DDF included, and that's something the whole community is welcome to help with, and we'll be happy to take your recommendations on that. Before I finish off my talk, I just wanted to highlight sort of a new scaling relationship. I know Shu presented in his presentation something that where they were using ZTF. That is also a bit of issue with being broadband filters, incorporating the different contamination, trying to mitigate this. We kind of applied a different strategy with Francisco and Eduardo from Max Planck by really using the performance of the Wi-Fi filters from the 2.2 La Silla telescope. This allows the incorporation of narrowband filters and optimize the positioning so that this can sort of be consolidated with LSST's light curve and kind of fill in the gaps where we do not really have the issues of seasonal gaps. The best thing that comes out of this analysis is that if we are measuring the carbon-4 accretion disk lag versus carbon-4 reverberation BLR lags, there is a factor of 165 times faster, more efficient analysis that we can do just with the photometry if done properly by optimizing filters. And eventually, I just want to leave it up here. So this is kind of the takeaway coming from this new relationship that we have found and published in APJ Letters last year, is that the BLR lags potentially, if you take about 16 years for a carbon-4 object, which has been done painstakingly by Shai Kaspi and his collaborators in the paper in 2021, where they re-established the carbon-4 radius luminosity relationship, including high redshift and high luminous age. This thing can actually be done of the order of months when we apply with the scaling, and then effectively gives a single epoch measurement of the black hole masses and the scaling that we are really looking forward to get the BLR sizes. So this is a kind of interesting thing that we have come up with, and we are sort of working progressively to include more and more objects into this campaign. And we are happy if you'll be interested and if you have any questions about it. Thank you.